Hopefully everyone already knows what I mean when I say greenhouse effect, because we've all experienced it, but I went ahead and pulled in a diagram showing the main ideas of the greenhouse effect here to start our video for today. So in this visualization, we are seeing that the wavelengths from the sun, short wavelengths including visible light and infrared, are impacting on here, but the infrared don't get through very well. Instead, we mostly have the visible light coming through, which we all are familiar with because we can see through glass windows. So the short wavelengths, the visible light, encounter the things inside of a greenhouse, or you might have experienced this more commonly in your car, and then they are absorbed by some of the materials. Also, some of the visible light reflects and goes back out again. But the visible light, once it's absorbed, it gets released again in multiple different modes. So it can be released as infrared radiation. It can be released as radio waves. Radio waves and other long waves can pass back out of the glass, but infrared doesn't travel through glass or through plastic very well. And the reason for this is that these materials are insulators. So glass and plastic are insulators. And this we are most familiar with in terms of electricity, but electricity and heat are both carried by electrons. And through the organized structure of the material called the lattice. And some of these lattices are well organized, and these would be crystalline materials. And others are not, they're amorphous, and glass is an example of this. Some plastic is crystalline too, but not all crystalline materials have electrons available to flow heat and electricity through them. So even those crystalline materials may not transfer heat and electricity very well. So glass and plastic are good insulators, and they keep heat in and they keep heat out pretty well. So bottom line, our infrared radiation can't pass back out of the greenhouse, and so it sort of accumulates in here and results in warming of the greenhouse. So that's the greenhouse effect in kind of a short version. And this is what we describe as happening in our atmosphere as well. So let's look a little bit more at the interaction of light and matter. We talked about this in the electromagnetic radiation video. And we're going to focus on infrared radiation here. In that electromagnetic radiation video, I talked about how when we have infrared radiation, what we're looking at is bond vibration if the molecule has a change in its dipole during the vibration. So just to make sure that everybody is 100% up on what we're talking about here, let's quickly review what we mean by a dipole. So a dipole is where you have a bond, and the two atoms in this bond have unequal sharing of the electrons. And let's say that we have a carbon and an oxygen here. And so if we have a carbon and an oxygen here, the oxygen pulls those electrons a little bit more strongly than the carbon does. And so that leaves us with a partial positive charge over here on the carbon and a partial negative charge over here on the oxygen. And if you want to visualize this, you can think about that bond. So this little blue bubble is going to be our two electrons, right, that are being shared by these two atoms. But instead of an equal sharing, we get more electron density over here on the oxygen and less electron density over here on the carbon. And that's where we end up with our partial positive charge from the lack of some electron density over here on the carbon and a partial negative charge on the oxygen as more of the electron cloud is hanging out by the oxygen. And the way that we pay attention to the difference between these two is based on the electronegativity of these two atoms. So let's just pull up an electronegativity chart here so we can quickly review it. I like this visualization of electronegativity because the relative heights are a little bit easier for me to interact with than just the numbers by themselves. So with electronegativity, this is, just as a quick reminder, a made-up scale. Most of them are following the Linus Pauling definition of electronegativity, which is the tendency of the electrons to hang out by one or the other of an element in a bond. I'm going to abbreviate this EN. And so if you don't have an electronegativity chart handy and you're trying to figure out a dipole, the easy way for me, and this is why I like this stair-step model here, is to remember that fluorine is the highest electronegativity and everybody is pretty much downhill from fluorine, and that you mostly get a more gradual drop-off as you go off toward the left and a more extreme one as you go down a column. But some of these are pretty subtle. Like these guys, silicon, germanium, and tin are all 1.8, and then lead goes up a tiny bit at 1.9, but we're not going to worry too much about those metals. Most of the time when we are talking about electronegativity differences, we are mostly paying attention to the nonmetals that we're interested in. And in terms of infrared absorbance, the reason is because you're not going to have metals forming gaseous materials for the most part. And so, we've mostly got carbon, hydrogen, oxygen, nitrogen, fluorine, a little bit of sulfur and phosphorus, and, maybe some chlorine, bromine. And then we're done. So you pay attention to the ones in purple, and everybody else is probably kind of off your radar. So when we're looking at a dipole, we're thinking about the differences between the electronegativities of the elements. And we're also thinking about the geometry of the molecule, because when we're talking about a dipole, we have two ways of talking about dipoles. We talk about bond dipoles, and then we have to think about net dipole. So if I'm looking at a molecule here, like formaldehyde, then I've got two different kinds of bond dipoles going on here. I have a carbon-hydrogen bond, well, two of those, and so if I look at the electronegativity difference here, carbon is 2.5 and hydrogen is 2.1, and so this is a slight difference. I would say that this is slightly polar. And then if I look at carbon versus oxygen, we have 2.5 again and 3.5. So our electronegativity difference is 1. And this is definitely a polar bond. But when we're looking at this molecule now, we also have the geometry that's involved. If you remember from your valence shell electron pair repulsion theory, this is a trigonal planar molecule. You mostly don't need to worry about the shapes of molecules because you can look them up. And so that means that this carbon-hydrogen bonds, each one of these bonds has a slight bond dipole here. where the hydrogens are the ones that are slightly positive, and the carbons, relatively speaking, are slightly negative. But then we also have the carbon-oxygen bond. This is going to get messy if I try and draw it on top of each other, so I'm going to draw it off to this side. So this carbon-oxygen bond is also polar, and in this case, the carbon is going to be on the positive side of this, and the oxygen is going to be on the negative side of this, since it's got the strongest electronegativity. So if we think about the polar, the net dipole for this molecule, you can see that the carbon-hydrogen-oxygen relationship here, we have two partners. We've got one partner, excuse me, this shouldn't be a little arrow with a plus on it. I'm going to redraw this down here. If we think about the polarity of this molecule as a whole, and we think about this molecule on three-dimensional or on two-dimensional axes, because it's a flat molecule, if I put my carbon here and my oxygen here and my two hydrogens here and here, then if I think about the dipoles here, I'm just going to draw these as arrows. These blue arrows are made up of a portion along the x-axis here, and this is my y-axis, and they also have a portion along the y-axis, right? So I can see that the two portions along the x-axis are, one of them is going in a positive direction, the other one is going in the negative direction, and so these two parts are kind of just going to cancel each other out. So the net direction of the dipole at this part of the molecule is going to be in the upward direction. And then from my carbon and my oxygen, this part of the dipole, this polar bond, is all in the same direction. So my total dipole, which is going to happen for the whole molecule, is going to just be in this same direction, heading along this y-axis symmetry point. Okay, so I only have one net dipole for the whole molecule, but it is a polar molecule overall, and each of its bonds are polar. And I want you to pay attention, molecule overall, and it has polar. My track record for writing and talking today is not great. Polar bonds. Okay, so this molecule has both polar bonds, and it is a polar molecule overall. And you can have one of these without the other, because as we just looked at here, remember how these two portions canceled each other out in the polar bond? You can have the polar bonds cancel each other out and give us a net non-polar molecule, even though our bonds are polar. And a great example of this is carbon dioxide. Carbon dioxide, we know, has a Lewis dot structure like this. It is a linear molecule. We just looked at that carbon-oxygen bond. And so we can see that our bonds are polar, where we would have an electronegativity difference. Our carbon would be slightly positive, our oxygens would be slightly negative. But because of the symmetry of this molecule, it is nonpolar overall, even though it has polar bonds. The symmetry is what cancels out the polarity of this molecule overall. So pay attention to those two things as two separate effects. So the infrared radiation, when we come back to that, we said that the infrared is absorbed when the dipoles change during vibration. That's our requirement. So we need to look at how things can vibrate. So we call these vibrational modes. And the way that we model these is that we think of bonds as springs. If we think about bonds as springs, then we can visualize how these molecules are going to stretch. So if we think about just two atoms bonded together, but instead of that straight line that I've drawn connecting them, we think about that as a little spring. Then if we just have these two atoms, we can see that pretty much the only thing that this bond can do is it can stretch. And this is one possible vibrational mode for a molecule. But once you add more than two atoms, then we start to get some different kinds of vibration possible. So if we think about two atoms, I'm going to draw them at an angle because it makes drawing a little bit easier. We can think about both these bonds stretching away from that central atom the same amount. This is called a symmetric stretch because it's stretching the same amount in both directions. But it doesn't have to do that. You can have one of your bonds stretching a little bit more while the other one stretches less. Or you can have this bond compressing while this bond stretches out. This would be called an asymmetric stretch. The other way that we can have these bonds vibrate is that we can have them start to bend. And there's actually kind of two different ways that we talk about these guys bending, but they tend to all have the same energy. So sometimes we'll call this bending, sometimes we'll call it wagging, sometimes we'll call it scissoring, and there are some slight differences in how we talk about each of these, but we aren't going to worry about the subtleties for this class. So each of these has different energies. And depending on whether or not the dipole changes while we have this vibration taking place, that will affect whether or not infrared is able to be absorbed by the molecule and trigger this kind of a stretch or a bend. So let's look at our main greenhouse gas that we tend to talk about, carbon dioxide again. And we already drew this molecule. And we already agreed that these bonds are polar, but that it has no net dipole. So let's look at the symmetric stretch. In the symmetric stretch, you're going to have these bonds stretching out and then back and stretching out and back, but they're going to be doing it at exactly the same time. And so it's still going to have no net dipole the whole time. So that means it does not absorb IR. If we think about the asymmetric stretch, then this would be where one of those bonds is more stretched in and the other one is a little bit less stretched in. And so in this case, because this bond is a little bit shorter than this one over this way, we're going to have a little net dipole off to the side, to one side. And as we stretch the other direction, we're going to have a little net dipole off to that other side. So yes, dipole does change during the vibration. And yes, we can absorb infrared. Now, the next one is when we're talking about bending. And this carbon dioxide molecule can bend. And when it does, then we're going to have a slight dipole. And so we're going to have the same conclusions that the dipole does change, and yes, we can absorb IR for both the asymmetric stretch and the bend. So let's take a look at a visualization of the stretching of the carbon dioxide molecule and also look at how that interacts with its infrared spectrum. All right, this is a diagram. Oh, this is a diagram of the carbon dioxide molecule showing the different vibrational modes. At the top, you can see the symmetric stretch shown, and then that one does not interact with infrared radiation, doesn't absorb any. But our asymmetric stretch, you can see over on the left-hand side, two different diagrams of what that asymmetric stretch might look like, and that corresponds to the infrared absorption peak. This is actually a transmission spectrum, and so absorption peaks are pointed down instead of up. So the absorption is happening at about 4.5 micrometers. And then you can see on the right-hand side a diagram of the bending mode for the carbon dioxide, which is over here on the right-hand side of the spectrum. That's that second set of peaks. Okay, so this is an example of carbon dioxide and its stretching modes. The next one we're going to look at is water. Water is already a polar molecule, and it has a net dipole even in its unstretched scenario, and it has three possible ways of absorbing infrared radiation. The symmetric, the asymmetric, and the bending stretches all absorb infrared radiation, and you can see where those are on their spectrum. So these are just two examples of different ways that molecules can interact with infrared radiation and absorb it. And you can also see that these spectra right here are listed in micrometers. But as we have mentioned before, we mostly talk about these infrared radiation in terms of wave numbers. So I'm going to switch back over. So you should remember from the electromagnetic radiation video that wave numbers, we use the nu with a squiggle over it, have units of inverse centimeter. And a wave number is just 1 over the wavelength, assuming that the wavelength happens to be in centimeters and not some other unit. So for the most part, for climate change, we are paying attention to the 500 to 1500 wave number range, even though many of these molecules do absorb in other ranges. So let's just take a moment and convert these wavelengths, or excuse me, these energies into wavelengths just to see what kind of a range that we were in, since that last figure had the had wavelengths for the graph instead of wave numbers. So go ahead and pause the video and calculate what the wavelengths are in micrometers for these two different numbers of wave numbers. Okay, hopefully you had a chance to do that, and you found that for 500 wave numbers, we have 20 micrometers for the wavelength, and for 1500, you should have about 6.7 micrometers for the wavelength here. So one of the things that I wanted to point out here that I think I've mentioned before, but I want to say it again, remember that smaller wavelengths are higher numbers, and higher wave numbers are higher energy. So higher wave number is higher energy, but lower wavelength is higher energy. Okay? I just like to always keep that in mind. All right. So we're going to take a look at the spectrum We've taken a look at this image before. This shows us the spectrum of sunlight at the top of the atmosphere. The black line is the black body curve at 50 degrees Celsius, which is maybe a little bit cooler than the calculation that we were estimating earlier for the sun. And then we also have this red line, which is radiation at sea level. And you probably noticed before that we have this yellow line, or this yellow curve, that's a little bit different in shape than this red one. That this red one has all this kind of like weird gappy stuff in it. So it's time to explain all of that crazy gappy stuff. This image is very much like the last one, only we have changed it into wave numbers. And now we've labeled where these gaps are coming from. And the gaps, so this blue part here, this is the same as that red part of the diagram before, only now we've labeled what's going on in here. So do you see this funny little gap that's right here? That is absorbance by carbon dioxide and ozone and nitrogen or dinitrogen monoxide. We have some differences over here caused by water. Ozone's over here, a little bit of N2O, a lot of methane, CH4, and a lot more water. Remember again that wave numbers are higher energy to the right on this diagram and lower energy on the left. And so this would be reversed from the scan that we just were looking at. So we have each of these different greenhouse gases that is absorbing different parts of our infrared spectrum and changing what's going on in our atmosphere. And do you remember how just a minute ago I talked about how we mainly pay attention to 500 to 1500 range? This is where we have the majority of the absorbance going on for the both the intensity and the gas activity. So that's why this range is especially important. So when we are looking at these greenhouse gases, we've looked at a few specific details here. Now I'm going to head back to the other screen. We're going to need to have some kind of overall effect for what the changes are to our energy. So remember that our equation before was represented sigma t to the fourth was equal to 1 minus, that was an A, not another sigma, omega over 4. And that this term on the left-hand side, this was our total amount of warming on the Earth. And then this term was the amount of warming from the sun. So we've been talking about the greenhouse effect, and it's clear that we need to add another term that is adding some additional energy due to the greenhouse effect, because we know from before that our total amount of warming was higher than just the amount of warming from the sun, because the temperature of our Earth was higher than the amount that was predicted just from the sunlight. So let's go back and calculate how much greenhouse effect warming we are having. We know that our temperature on average is about 288 Kelvin. And we know that this is a constant. This was the Stefan-Boltzmann constant. And then over here on the right-hand side, A was the albedo, which was about 30%. So in decimal form, that would be 0.3. Omega was the solar irradiation term, which was 1372 watts over a meter squared. And so we can solve for the delta E for the greenhouse effect just by plugging in the numbers that we have. So go ahead and take a moment and do that. Hopefully you got about 149.98, maybe you'd round it up to 150 watts per meter squared. So just to make sure that we are on the same page, the term that I got for the sigma t to the fourth, I calculated this total amount of warming previously as 390 watts per meter squared. And the term from the sun, that one came to 240.1 watts per meter squared. And so if we think about this term here and what proportion of the total amount of warming it is, it actually is pretty high. You can just divide 149 or 150 by 390. And if I do this, this turns out to be about 38%. So nearly 40% of the warming that is due to the Earth is due to the greenhouse effect that's happening in the atmosphere. So that means that some changes to the atmosphere could result in some pretty significant changes to our overall global average temperature, right? So imagine a scenario, for example, what if we had a situation where our albedo increased to 40% instead of just 30%? For example, in 1815, Mount Tambora erupted, and the next year there was a mini ice age in the UK. The global average temperature went down about half a degree, some places a little bit more than that. Now in the UK they didn't have any knowledge that there had been an eruption. They just knew that it was a really terrible growing season. They had way more snow than usual. Things froze that didn't normally freeze, because Tambora is, around the world from the UK. So clearly increasing the albedo would be pretty dramatic. So you can go ahead and calculate what the effect would be on the temperature of the Earth if you put in the albedo as 0.4 instead of 0.3. Leave everything else the same, even if that's not realistic. I mean, realistically, if we had a volcanic eruption, it would probably change the percentage of greenhouse gases. So there might be some warming to compensate from the increased albedo, but let's just go ahead and leave that. So pause the video, calculate that, and then come back in a moment. So hopefully you found that this temperature would be 281 Kelvin, which would be 7 degrees lower than 288. So that would be a pretty dramatic change. But you can also see why the theory that the dinosaurs went extinct after a giant meteor hit Mexico and caused an enormous dust cloud globally is actually plausible, because if you have something like a 7-degree drop, I mean, that's gigantic. And so you're going to have so much significant effect on the climate globally for a significant period of time. That's a pretty plausible explanation. So we're going to play around with some of these equations and with interpreting some of the infrared spectra. I've got a few useful links on the Moodle. There's one from the ACS Climate Science Toolkit website that has a lot of really interesting and useful information about climate change. Feel free to explore it. There's also a visualization website from King's University College up in Toronto, Canada, and they do a lot of work on visualizing climate change and also a whole bunch of other science topics, so feel free to explore their website too. I'll be posting a homework 10 that explores some of these concepts onto the Moodle, so keep your eye out for that.